Okay, time to record this lecture for the third time because it's been messing up. All right, so we are going to continue on with relations. Continuing on with relations. So this is section 9.1.5. So recall by definition, what is a relation? A relation from A to B is just a subset of the cross product. Is R as a subset of the cross product A cross B. Okay. Now, one important thing that I want for us to remark is that since R is just being viewed as a subset, we can actually perform all the usual set operations if we have several relations. So let R1 be some relation from A to B, which means A is R1 some subset of A cross B. And then let R2 be a second subset of A cross B. The point is, we can now define the union of relations, the union, intersection, the setwise difference. We can define the complement, right? All of these setwise operations are now available to us once we are just discussing subsets of A cross B. So let me give an example. I'm going to define 6 different relations, each of them relations on R. Remember when we say that a relation on a set is the same as a relation from the set to itself. So we're going to let Ri be relations on the set of real numbers. So each of these Ri is going to be a subset of R cross R. Okay? So let's set R1 to be equal to the set of all pairs or tuples AB in R squared, such that A is greater than B. R2 is going to be the set of all tuples such that A is greater than or equal to B. R3 is going to be the set of all tuples such that A is less than B. R4 is going to be the set of all tuples such that A is less than or equal to B. R5 is the set of all tuples such that A is equal to B. And R6 is going to be the set of tuples such that A is not equal to B. Okay? This defines a relation. Each of these defines a relation, but certainly not a function from R to R. And then we can discuss what are the unions of some of them. For instance, what is the union R1 union R3? Well, by definition, this is just going to be the set of all A, B in R squared such that either A is greater than B or the condition for R3, A is less than B. Right? I'm taking all of the elements in this relation, which is all the tuples such that A is greater than B, and I'm also taking all the tuples in R3, namely all the pairs A and B such that A is less than B. So this union of relations is actually equal to the relation R6, right? I'm looking at all pairs such that either A is greater than B or A is less than B. The only thing that's excluded is A equal to B. What else? Yes. Let's also consider R2 intersect, say, R4. R2 intersect R4. That means that we want the collection of all tuples A, B in R squared such that they're in the point AB is in R2, which means A is greater than or equal to B. And it also needs to be a point in R4, namely the tuple also must satisfy A is less than or equal to B. Right? So I need pairs A and B such that A is greater than or equal to B and A is less than or equal to B. The only option that's available here is for A to be equal to B. Sorry, this one should be R6, and this one's going to be R5, right? If A is both greater than or equal to B and less than or equal to B, then it must be equal to B. So this relation is the same as R5. If we look at something like R1 set minus R2. So let's look at all the tuples in R1, look at all the tuples in R2, and any that are in the intersection we remove from the set R1. But every tuple in R1 satisfies A is greater than B. Well, for every tuple A and B such that A is greater than B, that satisfies being in R2, because if A is greater than B, then A is certainly greater than or equal to B. So R1 set minus R2 is equal to the empty set. Every element in this relation is an element in this relation. On the other hand, if we reverse it and do R2 minus R1, then once again, we're going to be left with R5, right? Because if I take all elements such that A is greater than or equal to B and I subtract off all the elements where A is greater than B, I'm just left with the set where A is equal to B. Okay, so these are our usual relations, or our usual set operations that we like to perform, now being performed on relations, now being performed on subsets of a cross product. Okay. Okay. Next, we've got an interesting further operation that we want to define on some relations. Okay, definition. Let R1 be a relation from A to B, and let R2 be a relation from B to C. What we're going to define is the composition of these two relations. Then, the composition R2 composed with R1 will be a relation from A to C, defined as follows. R2 composed with R1 is going to be equal to the set of all tuples. Well, it's a relation from A to C, so I need to have tuples A comma C in A cross C. It's a subset of A cross C. And now we're going to say that it's the set of all tuples such that there exists a B in B such that AB is in R1 and BC is in R2. Okay. So this looks a little confusing perhaps, but when we draw a picture of an example, I think it becomes very clear. Let's let our set A, so example. Let's let our set A consist of the elements 1, 2, and 3. Let's let our set B consist of little a, little b, little c, little d, and let's let our set C be square, circle, and triangle. So to define a relation from A to B, essentially all I need are a collection of arrows pointing from the set A to the set B. So let me make a relation. I'm going to have one arrow pointing there and one arrow pointing there. I'm not going to have anything pointing away from 2. Then I'm going to have 1 pointing here and 1 pointing here. Why not? This is a relation from A to B. It's not a function for both reasons. First of all, 1 is not mapped uniquely to something in B, right? It's mapped to both A and B. So that's already not a function. And moreover, 2 isn't being sent to anything. So this fails both conditions for being a function. But then I make another relation, say, from B to C. So let's have an arrow go in there and an arrow go in there. And let's have C go into 2 places. Okay. This is some relation. Oh, let's make this one. Why not? So, okay, so this is R1 and this is R2. And the idea is that composition of relations essentially looks exactly like composition of functions. For instance, the tuple 1 comma square is in R2 composed with R1. Why? Well, there exists some element of B, namely A, such that 1A is in R1 and A square is in R2. So the composition takes the element 1A in R1 and A square in R2 and produces me one box in this composite relation. So it's exactly like what we did with functions. You make longer arrows by following through. I have an arrow now from 1 to square that passes through A. I also have a relation or an element in the relation 1 comma triangle for the same reason. I have 1 going to A and then A going to triangle. So I get that inside the relation. Notice there are a bunch of ways that I could get the same arrow, right? I could also go from 1 to B and then B to square. So 1B is in R1, B square is in R2. So that's another way that I could think of adding 1 square into this composite relation. We don't add it again because sets are just uniquely defined by each element. We don't take sets with multiplicity. Okay, so these two elements are in the relation, and then nothing else, right? Every other arrow, oh, no, just kidding. 3 goes to something. I'm going to have 3 square, and I'm going to have 3 triangle, right? But 2 can't go to anything, so there's not going to be any element 2 comma anything because 2 isn't mapped to anything. And then moreover, there is an arrow from 3 to D, but then D isn't sent to anything. In other words, D comma question mark is not inside R2. Right? There's no D squared, there's no D circle, there's no D triangle. So this arrow kind of dead ends. Okay, so this pretty clearly, this generalizes composition of functions. In other words, if these relations were functions, then this operation would just be composition of functions. Okay, definition. Well, not definition quite yet. So remember that we have these two different notations. We have a relation from A to B, but if A and B are the same set, we call that a relation on A. So if R is a relation on A, so R is a subset of A cross A, then we can compose a relation with itself. So let me give a definition. This is going to be a recursive definition of Rn. So I'm trying to define so this R power. So R1 will just be equal to R. So when I take R1, that's just the relation R in A cross A. Then I'm going to define Rn. This is going to be equal to R to the n minus 1 composed with R. Okay, so this is a recursive definition. It tells you once you have defined, say, R cubed or R to the fourth, then the way that you define the next one up is saying, well, R to the fifth is just R to the fourth composed with R. A very natural definition. Let's see this in an example. So let's let P be the set of all people. And I'm going to define a relation R on P is the parent relation. So R as a subset of, so R is a subset of P cross P. And in particular, R is going to be equal to the set of all tuples, A, B, in P cross P. A and B are people, such that A is a parent of B. Okay? So R1 is just equal to R. Set of all tuples, A and B, such that A is a person, B is a person, and A is a parent of B. Now let me define R squared. R squared, by definition, is equal to R1 composed with R1. And this is equal to the set of all A, B in P cross P, such that there exists a C in people, and A comma C is in R1, and C comma B is in R2. This is just by the definition. First I said, what is R2? By definition, it's R1 composed with R1. And then I just wrote down what is the composition of a relation. Okay. But if we parse out what this means, this is saying we're looking for all people A and B such that there exists a C, such that A is a parent of C, and C is a parent of B. So R squared is the grandparent relation. All the elements of R squared are pairs A and B such that A is a grandparent of B. Continuing on, we can go further, right? R cubed is going to be equal to R squared. Oh, I'm sorry. R cubed is going to be equal to R squared composed with R1. By definition, this is going to be equal to the set of all pairs A, C in P cross P, such that there exists some B such that AB is in R squared and BC is in R. So what this is asking for is A comma C is in P cross P if A is a grandparent of B and B is a parent of C. So this is great grandparents. Okay. And of course, since these are all relations on the same pair of sets, namely R3, R2, and R1 are all subsets of P cross P, we can do unions, right? R3 union R2 union R1. This is precisely equal to the set of all pairs AB such that either A is a parent of B, A is a grandparent of B, or A is a great-grandparent of B. A, B, such that A is a parent, grandparent, or great-grandparent of B. Okay, so this is something that we got by both composition of relations and unions. And similarly, we can define, more general unions of sets. Remember, relations are just subsets of a cross product, so can do the union of I equals 1 all the way up to infinity of Ri. So this is R1 union R2 union R3 union R4, etc. So this is either A is a parent of B, A is a grandparent of B, great-grandparent, great-great-grandparent. So this relation should probably be called the ancestor relation. So A comma B is inside this set, which is a relation, if A is an ancestor of B. So that's kind of nice. It's good to think of grandparents at this time. Okay, what next? Yes. Next is the following. There's a nice kind of relationship between this composition of relations and transitivity. So that's the last thing that I want to discuss here. So here's a theorem. So a relation R on A, so remember this means R is a subset of A cross A, or R is a relation from A to A. Relation R on A is transitive if and only if the following holds. If and only if R to the n is a subset or subrelation of R for all n greater than or equal to 1. Okay, so the first thing that we should do is remember off to the side, what does it mean for a relation R on A to be transitive? So transitivity, this is something we covered in the last lecture. If A comma B is in R and B comma C is in R, then A comma C is in R. This is what it means for a relation to be transitive. Notice that our relation that we defined up here, the parent relation, is certainly not transitive. Okay, so now that we have our definition, we're going to prove this in 2 steps, right? It's an if and only if statement. So I'm going to first prove one direction. I'm going to assume that Rn is a subset of R for all n, and I'm going to show that that implies that the relation R is transitive. So assume that Rn is a subset of R for all n. In particular, this implies that R2 is a subset of R, right? R2 is just one of these Rn's, and we know that all of them are subsets. Okay, so let's show that R2 being contained in R is equivalent to R being transitive. So assume that A, B, and B, C are in R. Now, we don't a priori know that AC is in R yet, but we do know that AC is in R squared. By definition, AC is in R squared, since there exists a B that does the trick, right? So I'm assuming that I have 2 elements that are set up for the transitivity property, and now I show that if I have 2 such elements, then I have AC. Well, AC is in R squared by definition, but if we assume that R squared is a subset of R, then thus R squared, thus AC is an element of R, since R squared is in R. So every element of R squared must be an element of R. So R is transitive. Okay. So this proved one direction. I assumed the second statement and showed that it implied the first statement. Now I need to go the other way start with the first statement and show that it implies the second statement. The second direction is going to be proved by induction. So I'm going to go this way. Assume R is transitive. We show R to the n is a subset of R for all n by induction. Okay, so there are two steps that we need to do for the induction. One is we need the base case. The base case here is we want to show that R to the 1 is a subset of R. This is true since R1 is equal to R. So R is certainly a subset of R by definition. Trivially, I should say. R is always a subset of R. So that's the base case taken care of. Now we need to do the inductive step. For the inductive step, we will assume that Rn is a subset of R, and then what I want to show is that Rn plus 1 is also a subset of R. So in my scratch work off to the side, I want to show that Rn plus 1 is also a subset of R. Okay. So if I want to show that R plus n is a subset of R, I need to start with an element. So let AB be inside R n plus 1. Remember, all these relations are subsets of A cross A. So I've got little a in A and little b in A. I've got an element of this relation. And I want to show that AB is actually in R. Okay, so by definition, what does it mean for A comma B to be in Rn plus 1? This means AB is in Rn composed with R. For A and B to be in a composition, thus there exists a C such that AC is in Rn and CB is in R. Right? This is exactly what it means to be inside a composition. If A comma B is inside this composition, it means there exists a C such that the first pair is in the first relation and the second pair is in the second relation, and you think of the two middles as being the same. So you follow an arrow from A to C, and then you're going to follow it through from C to B and get A comma B in Rn plus 1. Okay. Now, by assumption, here's the inductive hypothesis. By assumption, R to the n is a subset of R. So we have AC in R, not just Rn. AC is in R, and now CB is in R. By transitivity, of R, if AC is in R and CB is in R, AB is in R. And you should say a little more at this stage, like, thus the inductive step is proven, and then thus we have finished this proof by induction. But essentially, what we set out to show is that Rn plus 1 is a subset of R. We started with an element of Rn plus 1, namely A comma B, and then we showed that that element is also an element of R. And this is how we show containment of sets. Okay? So that's a nice relationship between the transitivity property and composition of relations, which generalizes composition of functions. All right, I think that's going to be all for this lecture. I hope that this format of the DocCam is going to work out okay. I know it's not optimal, but Yeah, there's nothing more to say. It's not optimal. Sorry for this change of format. Once again, let me know if you have any questions. I'm happy to respond to comments on YouTube. I'm happy to respond to emails. Yeah, let me know if you have any questions.